And as much as Art's impact is on the profession, I think his impact has equally been on the colleagues he worked with and on the students that he advised and mentored, a number of whom are with us here in the room. And we're also, I want to acknowledge your role, Art, in being one of the founding members of the Asian Institute of Technology. So Art's here with us this evening. Let's all give Art a round of acknowledgement and thanks. Art, we're deeply honored with your connections to CSU, and we're even more pleased that you could join us here this evening. I want to acknowledge and thank a number of individuals that played a key role in helping us create this lecture series. I'd like to thank John Nelson, importantly, Subin Pinkayan, and Anat, help me, John. Arbaparam, all of whom have connections, strong connections with Art over the years. And I also want to acknowledge and thank Engineering Analytics, who sponsored the reception this evening. And so, John, if you would, could I actually have you come up and announce and give a brief introduction to our speaker this evening?
Well, this is a pleasure and a privilege to be here. Art Corey is kind of a special person, and the doctor in Thailand they only use the first names. So Subin Pinkayan is actually Dr. Subin, and Anat is Dr. Anat, and I'm just Kun John. But when I went to AIT in 1968, Subin and Anat and I were young assistant professors, and we taught together and became very good friends. They took me under their wing and taught me all about Thailand, Thai ways, and so on and so forth. Now, Art Corey was a very special person for all three of us. First of all, with Subin, when he got his master's degree at AIT, he didn't know where he wanted to go, what he wanted to do, this, that, and so on. And Art got him over here, said, I might be able to get a little bit of funding for you or not, but Subin actually lived with Art for a couple of years when he first came as a young lad. Anat got his master's degree at AIT with Art there, and Art brought him over. Now, Subin's advisor here was Dr. Yevgevich. A lot of you remember Yevgevich, Dr. Y. And Art was Anat's advisor for his PhD. Well, I came back in 1973, and I decided I was going to start doing some research in expansive soils. But you see, over in Thailand, all the soil is saturated and it's soft. And over here, all the soil is unsaturated and it's really hard. But when it gets wet, it expands. But it expands because the water gets into it, and I had to learn about unsaturated, movement of water in unsaturated soils. Art was a mentor to me on that. I remember one day, I met him in the hallway. I asked him a simple question. We ended up finding a classroom that was empty, and 2 hours later, we said, okay, well, I'll talk to you later some more. So anyway, Art was a very special person. Now, also when I got here, I met another man named Dr. Mcwhorter. And Dr. Mcwhorter and I got to be good friends. And we did some work together. And he and I collaborated on a paper to teach civil engineers and mining engineers how to analyze seepage of water from tailings impoundments in the unsaturated zone. Now, when I say we collaborated on that paper, what that means is that Dave wrote it and then I read it. I told him also that the geotechnical engineers call that this, not that. And so we did do a little bit of language working on it so that the geotechnical engineers would understand it. Dave and I got to be good friends. We did consulting together, and And as it turns out, he raises horses and I raise cows, so we also have a little bond there. But Dave has always been a good colleague. It's a real privilege for me to have been a colleague of his. He's done a lot of very good work on movement of water in soils and movement of contaminants and immiscible fluids, which means they just don't mix. So anyway, it's my pleasure then to introduce Dr. David B Mcwhorter.
Well, good evening, everyone. Thank you so very much for coming to honor Dr. Corey tonight. I'm especially grateful that I have this opportunity to express my gratitude to Dr. Corey for all the things that he's done for me. Dr. Corey is a true scholar. Back in the 1960s, he recognized that the traditional concepts that surrounded the idea of a total potential were incorrect, and he wrote a paper for which he was accused of violating the basic tenets of thermodynamics. Remember that, Art? But he didn't, of course. And eventually his ideas prevailed there. As recently as 2003 and 2005, he's published peer-reviewed papers dealing with the theory of the simultaneous diffusion and advective transport of solutes in water. And only 10 days or so ago, I received a paper on my email from Art, a draft paper, that is challenging some of the closely held interpretations of the Navier-Stokes equation for non-homogeneous fluids. And Art's 6 years old, so I hope that all the rest of us will be able to think like he can when we're at that age. When Dr. Corey's mind isn't occupied by technical matters, he thinks and cares for his family, his students, and his friends. Well, it's actually several years ago now. For his 80th birthday, we had a get-together, and Dr. Deanna Durnford, who many of you know, told the assembled that Dr. Corey used to spend untold hours in the laboratory with her, teaching her the intricate measurements that Dr. Corey was actually famous for. And she couldn't understand why she was so special. And then she said, I got to thinking, and I realized that all of Art's students are special to him. And that is absolutely true. And more than once, my wife has said that she thinks that Dr. Corey is the perfect professor. And I agree. Art, my own life has been immeasurably enriched by knowing you and studying under you. And I want to thank you for that. And on behalf of the many students that are here and are not here, I'd like to thank you for them as well. I'm going to talk tonight about the Santa Susana Field Laboratory in Ventura County, California. This is undoubtedly one of the most high-profile sites, contaminated sites in California and possibly in the nation. There were two primary functions at the Santa Susana Field Laboratory. One of them was conducted by the DOE and its predecessors in nuclear research. They studied sodium and other liquid metal cooled nuclear reactors. But I'm not going to be talking about that aspect of the site. I'm going to focus tonight on the rocket engine testing that went on there. It started as early as the early 50s and went on until 2006. The rocket test fuel that was used there was a liquid oxygen kerosene mix, so maybe some of you have heard of the perchlorate problems that have occurred in other places where they've used rocket fuels. That doesn't enter into the picture at this particular site. About over 20,000 tests were conducted there, most of them between 1994 and 1954 and 1966. That was the intense period when these tests went on. The Santa Susana Field Laboratory is located near the coast, about 35 miles north of the center of Los Angeles. It's an upland area. On the north is the Simi Valley, and on the east side is the San Fernando Valley. It is surrounded by a variety of communities, including Simi Valley, Chatsworth, Canoga Park, Woodland Hills, Thousand Oaks, and if I could have a pointer that would work real well, I could point out where Calabasas is. It's down in kind of the left right-hand corner, or excuse me, the right lower corner of that picture. And you'll probably be glad to know that that's where Justin Bieber lives. Most of these communities are upscale, and some of them are actually off-scale. And the entire site is, virtually the entire site, is underlain by the geologic formation known as the Chatsworth Formation. It's a sandstone with shale, and it is represented by the yellow area in this geologic map. This is a picture of one of the outcrops of the Chatsworth Formation. Note the huge blocks separated by sizable fractures. Some of these fractures you can actually stick your arm in. In some cases you can even walk back into some of these fractures. The Chatsworth Formation geologically is a late Cretaceous deep sea turbidite deposit, in case you wanted to know. And it's actually a beautiful area. It's a really nice area to work. Even though it's in a very populated, highly populated area, it's wild. There's wildlife everywhere. Very reminiscent of the kinds of topography and landscapes that you used to see in the old westerns. You almost expect to see John Wayne come riding around an outcrop on his horse at any moment. The engines were tested in these very large, enormous steel structures called test stands. This is a picture of one of them. And these test stands were located in 6 different locations on the Santa Susana Field Laboratory. And each location had multiple of these test stands. At the peak of their operation, they tested 3,000 engines in 1 year. That's almost 10 per day, and some of these engines actually had thrusts of well over 1 million pounds. So these structures were really very, very impressive. And unfortunately, they don't exist there anymore. They've torn them all down since 2006. I have a little piece of one, though, that was embedded in plastic and given to me as a memento for my work there, and I treasure that. It's a great memento. The interested parties here were Boeing, NASA, and DOE. Originally, this site, when I first came to know it, was operated by Rocketdyne, which was a division of Rockwell International. Boeing bought them in 1966, and so my experience there has been almost entirely with Boeing. The primary regulatory agency for the groundwater work is the Department of Toxic Substances Control, or the DTSC. This is a division of the California EPA. You might just note that this is not a Superfund site. There are sincere and rational citizen groups that are interested in seeing that this site is closed in the correct way. We enjoy working with those folks. These groups are sandwiched between fringe groups that have their own agenda or no apparent agenda at all. And then we have, on the other fringe, irrational individuals. One night, Dr. John Cherry was giving a talk at one of our public meetings, and this woman stood up and she said, Dr. Cherry, have you ever used Einstein's theories on this site? She says, I have the web pages right here. I'll give them to you so you can study how to apply them at this site. And John never cracked a smile. He just said, well, ma'am, I'm not sure how Einstein would think about this site, but, and he went on with his lecture. So there's a core investigative team that I've been involved with since 1996. And these are the main players in that core team. The advisory panel is made up of John Cherry, myself, and Beth Parker. John Cherry is a distinguished professor emeritus from the University of Waterloo. He's probably the most recognizable name in hydrogeology in North America and Europe. Beth Parker is a professor and industrial research chair at the University of Guelph. And she actually attended CSU here and studied with me for 6 months back in 1992. She knows Dr. Corey and remembers him, and she said to say hi. So I've done that. Both John and Beth are really co-authors of this talk. They are responsible for a good many of the ideas on the project and a good many of the slides I'm showing tonight. When I use the word we from now on in this talk, it's really an editorial we. I'm including all of those that have contributed. When we first arrived at the site, this is a view that was presented to us as we drove up towards the site. The big rock outcroppings and the big cracks are unmistakable and very, very impressive. It's not too difficult to imagine why the public might think that these cracks have a huge impact on the way contaminants move off of the site and into their communities. And in fact, our first step was to look at the groundwater issues at the site as a first step towards dispelling the idea that these fractures gushed groundwater carrying all kinds of contaminants out into their communities. And so these are the items that I'm going to go through rather quickly here in the next few minutes. And my memory's not even as good as Dr. Corey, so I have to have a cheat sheet. Oh, one thing I've already forgotten to say, I'm going to back up here a moment. This panel, we started in 1966 when this, the operator of this site was Rocketdyne. And there was a man by the name of Steve LaFlamme who was a division director there and then went on to executive positions in Boeing after we left. But he was the one who hired us, organized the panel, hired us, and he's the one that championed the scientific approach to this site, which is substantially different than occurs at many, many contaminated sites across the country. And by a remarkable confluence of circumstances, Steve LaFlamme is here tonight. And so Steve is here, and he will be available to ask questions of after this. I'm assuming that you'd be available. Well, we drove up the hill that afternoon after being invited to come and look at the site. And the first thing we recognized that there was really quite a lot of wells already available on the site. They were just everyday, traditional monitor wells, and you can see that by now there's a lot more. But the interesting thing is that we found that the water levels in these wells was on the order of 50 to 100 feet below ground surface. And this gave us an opportunity to make some calculations, because there's a relationship between the water level in a mountain like this, in a groundwater mound, and the resistance to flow, or the ease with which water flows through the material, which we call the permeability. And you can formalize that relationship a little bit, and we call this the Meatloaf Model. And that was actually named after me because I liked meatloaf, and we had a special place that we went to eat many times there. And it's shaped like a meatloaf. And with just some topographic measurements and an estimate of recharge by taking a percentage of the average annual precipitation, you can make an estimate of what the bulk overall hydraulic conductivity is of the mountain. In this case, it turned out to be about 1 times 10 to the minus 5 centimeters per second. For those of you that don't speak groundwater as a first language, the hydraulic conductivity is the term that we use for measuring how easily water flows through a porous material. And this is a moderate value, moderate to low actually. This is not the kind of value that you would want if you wanted to establish an irrigation well or even a domestic well. So there's already some evidence that those big fractures that we see and are so prominent really aren't having a huge effect on the way the groundwater flows. But how does the groundwater actually occur in this aquifer, in this sandstone? Well, the large fraction of the water occupies the interstitial pore space between the sand grains in the matrix blocks that are bounded by the fractures themselves. And we can measure that porosity by taking a number of core plugs from these matrix blocks and take them back to the laboratory and measure that porosity by various methods. And we did that on about 137 samples. These are the results of that. Over on the right side of this graph, there are numbers for the unconsolidated sands and the near surface materials. Down in the middle of the aquifer, down in the real deep bedrock, the average porosity is about 13%. So that means that 13% of that total rock volume is void space that is filled with water, that is otherwise filled with water. Now that doesn't account for the fractures. We have a dense, well interconnected network of fractures in this system. And our measurements would indicate that we have from 2 to 3 fractures per meter. That's about the frequency. And you can't see that many. When you walk out and you look at the outcrops and the subcrops and so forth, you can't see that many fractures, but that's about the frequency that we get from televiewers, geophysical logs, and from cores. So water fills the fracture porosity as well, but we can't measure the fracture porosity directly. There's no way that you can bring big enough sample back that you have a representative number of fractures and so forth that you can actually make these measurements in the laboratory, or without at least tremendous expense. Maybe even Boeing doesn't have that much money. And but you can make an estimate of what the fracture porosity is by postulating some hypothetical models for fracture geometry, whether they're orthogonal and so forth, and the distance between the walls of the fractures. And when you do that, you get a number which is negligible compared to the storage volume that's contributed by the interstitial porosity in the matrix blocks. So the fractures aren't important at all with respect to how much water there is in the mountain. On the other hand, fractures are very important with respect to how the groundwater moves, in spite of the fact that we already are suspicious that the big cracks don't have much role to play. So how do you go about measuring the hydraulic conductivity of the fractures? Well, we really can't, not directly. But we can measure the hydraulic conductivity of the matrix from those samples that we've taken in the lab. Those are the numbers over on the left. That's this equation on the left side. Over on the right side of this graph is the equation that we would use to calculate what we call the bulk hydraulic conductivity. That would include contributions from both the matrix and from the fractures. And we can subtract the two and we get what the fractures are. But it turns out that's not even necessary, because the bulk hydraulic conductivity is so large relative to the matrix hydraulic conductivity that for all practical purposes we can call it the bulk hydraulic conductivity equal to the fracture hydraulic conductivity. And here's some data to show that this is in fact true. On the far left there are the core samples from the matrix material, and you can see there that we have about 5 times 10 to the minus 7 centimeters per second hydraulic conductivity in the matrix. The bulk hydraulic conductivity is anywhere from 1 to 2 orders of magnitude higher than the matrix hydraulic conductivity. So even though the fractures don't occupy much pore space, they control the flow in the aquifer. And why is that true? Well, the matrix voids are very small. And even though there's a lot of them and they hold a lot of water, they don't let water flow through them very easily because of the size of the openings. On the other hand, the fractures are kind of sparse in relation to what the matrix voids are, but they're much larger in size. So water can flow more easily through them. And we characterize these cracks or these fractures by the aperture. The aperture is simply the distance between the walls of the fracture, and you can see that it's highly variable as you go from place to place along this block of sandstone. And in fact, we can't measure the aperture directly, so we cheat. We introduce a concept of what we call the hydraulic aperture. And we imagine a smooth-walled fracture which will carry exactly the same flow as the actual rough-walled fracture under the same driving force conditions. And that allows us then, using what is called the cubic law, to back calculate the aperture of the smooth-walled fracture. But that means, of course, that we have to actually measure the flow rate in the actual fractures first. And we've done that by a variety of methods. The Packer method is a very common method. This is straddle packers are used to isolate a narrow zone within the aquifer, one fracture, maybe 2 or 3 fractures, hopefully not more than that. We induce inflow or outflow between those straddle packers and measure the response in the aquifer, and from that we can calculate what the aperture is. We also use an innovative method. It's called Flute profiling. Flute stands for Flexible Underground Technology, and it's a liner that is kind of like a sock that is rolled up on a reel and wrong side out. And you attach the first part of that liner to the top of the casing with a steel band. Then you begin to add water into this space that's created at the top. It unreels the liner into the hole and creates a seal behind the inverted point that goes downward in the well. The water that's already in the well gets displaced as this liner moves in, and the rate at which it gets displaced is dependent upon how the transmissivity or how permeable the material is below that inversion point. And when you cross a zone of significant hydraulic conductivity or permeability, the rate slows. And by noting or measuring the change in the rate, we can actually calculate the hydraulic conductivity of these fractures. And then back calculate the the aperture, the hydraulic aperture. We've done this on over 900 situations, and our typical range for these fracture apertures, hydraulic apertures, 70 to 100 microns. This is just about the size of a human hair. So you can't even see most of these. Yet these are the fractures that are controlling the flow in this aquifer. It's not those great big ones. So where does the water come from that's in the aquifer in the first place? It comes from rainfall, almost entirely in this case. We've used various methods to try to estimate what this recharge is. This remains a controversial point. The technical people in the regulatory agency do not believe our estimates. They think it's much higher. But we have really pretty good evidence that the recharge rate is somewhere between, say, 1/2 inch per year and 1.3 inches per year over the entire footprint of the site. And if you take the entire footprint of the site, which is about 2,850 acres, and convert that to gallons per minute, we get a pretty modest flow rate out of the aquifer. So where does this flow go? Well, about half of it goes to the springs, seeps, and phreatophytes that exist all around the edges of the mountain, and about half of it goes to deep aquifer or deep aquifers and completely out of the picture. We know this because we have built perhaps one of the largest finite element groundwater flow models in existence, and it's from those models that we make these estimates that it's about a 50-50 split between these two discharge zones in the aquifer. Here are some pictures of the seeps and springs. We called them springs to begin with till we got to looking. Then we called them seeps. They're not really springs in most cases. Phreatophytes all over the top of the mountain and along the edges. It's really a very beautiful area. This is a map that shows at least some of the locations of the seeps and phreatophytes around the site. We've now identified 165 separate springs and seeps. And a little later I'll talk about what we do with those seeps. So now I'm going to transition into the freight and transport portion of the talk. And these are the items that we're going to be taking up. The contamination I'm going to be talking about is contamination from trichloroethylene. We call it TCE. TCE is a very effective solvent that was used to flush these engines pre-test in order to be sure there was no residual carbon or other contaminants in the engine, which was cause an explosion when the liquid oxygen was introduced. So that was the primary reason for that. CH2M Hill did a study a few years ago to try to estimate how much TCE might have been used on this site and what might have happened to it. They estimated, by going back through all of the records, that about 1 million gallons of TCE was used in this flushing process up until about 1962. And then in 1962, we still used TCE, but they introduced a catch pan system that would keep the TCE from just flowing out the flame deflector and going down into the draws and eventually into the groundwater aquifer. And when asked how much of this TCE might have gotten into the groundwater aquifer, one of the former employees of Rocketdyne simply said, well, I think we evaporated about half of it. And 500,000 gallons is the number that has stuck in everyone's mind ever since. And so we live with 500,000 gallons of TCE in this aquifer, and we don't believe there's anywhere near that much there. But if we can't account for the 500,000 gallons, then the public thinks that it's out there under their homes and other places in the community. So this has been a major problem for it. How does this TCE actually get into the aquifer then? After the flushing operation, they just let it flow out of the flame deflector, and it flows down a gunite channel, as indicated in this cartoon to the left, and then goes into holding ponds. And these holding ponds were unlined, and TCE is immiscible fluid, and so it doesn't mix with water, and furthermore it's more dense than water, so it flows right to the bottom of these holding ponds where it seeps in into the fractures that are intersected by the bottom of the pond. The TCE is oftentimes called DNAPL. It stands for dense non-aqueous phase liquid. Mercury is probably the granddaddy of all DNAPLs. The term DNAPL comes from the Love Canal litigation that happened years and years ago. But essentially, it just simply means that the TCE is more dense than water and it won't mix with water. These light blue areas shown on this slide are the artist's conception of where TCE exists in the aquifer at this time. And you can see they're just kind of spread all over. And now, how does this next three slides are kind of the centerpiece of our conceptual model for this site. When the DNAPL first enters into these fractures, it moves downward because it's more dense than water, and so gravity tends to move it downward through these fractures. And remember, the fractures are fairly permeable, as we've already discovered, so it could be expected that this DNAPL might go rather deeply into the aquifer. But it also begins to diffuse, dissolve, I should say, into the contiguous water. So the DNAPL that's in these fractures is also in contact with water on the boundaries and elsewhere in the fracture, and some of it dissolves. And pretty soon some of the DNAPL in the fractures begins to break up and become little globules and so forth, and they don't move so rapidly anymore. And this is what we call stage 2 of the process. But you'll notice that towards the right there are some fractures that have dissolved TCE in them, but don't have any DNAPL. And that portion of the picture grows with time. And finally, you reach stage 4, where there's no DNAPL left, and the entire plume is comprised of dissolved DNAPL that is diffused into the matrix blocks adjacent to the fractures. Now, this diffusion process is really highly important. I don't know how to overemphasize how important it is. If you just examine the rate of flow of fluid, like water, in one of these fractures, you'd find that the velocity is on the order of miles per year. It really moves on out. But the dissolved plume that is pictured in this cartoon moves much, much more slowly, as I'm going to show you. Well, how do we know that this hypothesis, which is what it was, is correct? Well, we embarked on a core drilling project. To date, there have been 20 core holes drilled now. And this slide represents Beth Parker's method for analyzing these core data to understand where the TCE is in the matrix blocks adjacent to the fractures. So the first step is core extraction. You get a full core out of that. Then you sample that core, you crush it, and dissolve and place it in a bottle of methanol, which extracts the TCE from the pores. Then you can measure the amount of TCE, and through some relatively simple calculations, you can present the data in this way. This shows the TCE concentration at various points in the sandstone. This is the first, I think this is the first one that we did there. And as a function of depth, note this is a log scale across the top. That bold dotted line over on the right is the solubility of TCE in water. All of these numbers are lower than the solubility of TCE in water, but some of them still get pretty large. And you can see that the distribution of TCE is spiky. It has gone down one of these fractures, diffused into the matrix blocks, and because the fractures are only occur in intervals, so does the TCE. We have over 7,000 of these measurements now made with 20 core holes. I just want to show this slide to indicate that, in fact, we believe we found the bottom of this. That was one of the big problems when we went to this site. TCE being more dense than water, you might expect it to just go a long, long ways down. Well, it went down to maybe at least 1,400 feet, so maybe that is a long ways down. That's well below sea level at this site. But almost none of the values in this 7,000 exceeded the solubility of TCE in water, so we're almost certain that no DNAPL now exists. We better understand and bolster our knowledge about this site by looking at selected models. This is the fracture network that we input into a model called FracTran that was developed at the University of Waterloo. It's a discrete fracture model that calculates the water flow in the fractures and the contaminant transport with full consideration of the tendency for the dissolved TCE to diffuse into the adjacent matrix blocks. I'd like to tell you a little bit about that model, but it's probably too technical. It's an amazing little model. The only problem with it is it's two-dimensional, but we have to live with that because it's so useful in other ways. But we input to this model a random distribution of fractures, both vertical and horizontal. They have to be orthogonal, and that distribution of that random placement mimics the statistics of our actual field data. And then up on the upper left-hand side, we impose a TCE source at the solubility limit, which is about 1,100 milligrams per liter or so, and we allow groundwater to pass through this and see what happens. And you can't see the numbers on the bottom of this, but the right-hand side of this is 1,000 meters, 100 meters down the stream. No, it's 1,000 meters, yeah, 1,000 meters downstream. And it shows the progression of the plume over a period of time. And you can see that even after 100 years, it's gone less than 1,000 meters. Furthermore, it's slowing down. It doesn't go nearly as fast in the last 40 years as it did in the first 40 years. And that's all a result of this matrix diffusion. So once again, I'll emphasize that the flow of the water in the fractures is miles per year. And here in 100 years, the TCE that's contained in that water has only moved something on the order of a half a mile in 100 years. Well, is this reasonable? We took a closer look at what we call the Northeast Plume. We built a whole number of core holes, took very careful data, as indicated along this black line here. And I won't go into the details of this, but this is what that plume looks like. The front of that plume, which we believe to be the longest plume on the site and in the most permeable area, has only gone less than 3,200 feet in about 50 years. So that was a kind of a confirmation of our hypothesis. To further confirm our hypothesis, we decided that we needed to examine the seeps, because any groundwater hydrologist or hydrogeologist will tell you that's where the water is going. And out of those 165 seeps that are existent on the site, we sampled 58 samples for site contaminants, 58 seeps for site contaminants, and we didn't find a site contaminant in any of them except for 3 seeps that were on site. All the off-site seeps were free of the contaminants from the site. Actually, that's not quite true. We did run into a lot of poison oak. But how do you rule out false negatives? This was a big problem because TCE in water is volatile. And so it might be that we didn't detect TCE because it had volatilized, or perhaps we're measuring bank storage due to a previous rainstorm or some other reason. So we embarked on a drilling program, and we drilled 17 seep locations, and we established 53 sampling locations in those seeps. or in those drill holes, and we didn't find any contaminants in any of the off-site locations in these seeps there either. And we pretty well laid to rest the question of whether or not we're getting false negatives. By the way, this is all further bolstered by looking at tritium, but I'm probably already running over time. I'm not going to talk about the tritium tonight. The access to these seeps is a challenge. You may have heard the old adage that what you overlook will come back to bite you. In this case, it was rattlesnakes. And we had to backpack these drilling rigs into these seeps. A major undertaking to get this job. In one particular one, we actually flew it in on a helicopter. So, there are key ongoing studies that still are yet to be completed. Natural, chemical, and biological degradation is a major player at this site and is something that Tom Sale encouraged me to talk about, but it's not my daily work. It's not my bailiwick, so I elected to, and I knew I wouldn't have time anyway. But that's a major study that's ongoing. We are looking at starting to look at some possible remediation technologies. In situ chemical oxidation is in a pilot stage at one site. We've done some pilot bedrock vapor extraction, and we've done some paper studies on thermal remediation. And site characterization is still going on. The findings that we've made are numerous. I'm just going to give you just these few. All the TCE mass we now believe is in the matrix. Hardly any of it is in the fractures. This matrix diffusion limits the rate at which these plumes expand and move down gradient and cause these plumes to be very small, actually. And most of the TCE is within very close proximity to where it went in the ground in the first place. We feel very confident that TCE has not escaped via groundwater into any of the adjacent communities. Surface water may be another story, but we didn't study the surface water. And the TCE is effectively trapped. All of these are prompted one lady at one of our meetings to call the Chatsworth Formation John Cherry's Magic Rocks, because it seemed like all the problems were solved. There are a huge volume of publications that have come out of this study. Most of them are open to the public. I could help people get them if they are interested in looking at them. They're pretty boring, really, for the most part. But when will the project end? Well, the project will end when there's a consensus among all of the interested parties that we've done enough. And that requires trust. And at the moment, the regulatory agencies are operating in the mode that one test is worth 1,000 expert opinions. And that has caused us to go slower than we would like to. And we were told by an expert in the matter that the public puts their most trust in firefighters. Consultants, not so much. And it reminds me of a book I just read not so long ago about starting cults. And it went paragraph by paragraph and page after page and chapter after chapter, telling you all of the things that you should do to minimize the chances of getting bucked off when you got on this cult for the first time. But the foreword to this book was written by an old Wyoming cowboy, and he said, all that's well and good, but at some point you got to hike up your chaps, pull down your hat, and get on. And I think that's where we are. Thank you very much. Are there questions? Yes.
You had a few slides where
Yes.
So, how different in terms of orders of magnitude do you think it is between the unsaturated zone versus the saturated zone?
Well, in the unsaturated zone, the TCE in the liquid form, the neat TCE, occurs almost entirely in the fractures, but not entirely like it does below the water table, because there is some airspace in the vadose zone by definition, and the TCE is what we call an intermediate wetting fluid, so it will tend to displace some of the air that is present in the pore space and move into those zones. So we do have liquid TCE in matrix blocks in the vadose zone, or in the unsaturated zone, which we believe never happens below the water table. But on the other hand, the TCE in the matrix blocks in the vadose zone is accessible by air, so we can force air through there and we can volatilize it. Yes.
I'd like to, my name is Langenbach. I'd like to sort of make this opportunity to thank and ask a question first, because I think a lot of the names you were mentioned during John's introduction, I was sort of associated with those people. Actually, I learned my groundwater from Dr. Mcwhorter, and then so I have some connections to Corey. Actually, he started AIT. I was the first Sri Lankan to go to AIT, and these young professors were my professors when we were at AIT. So I really want to use this opportunity to thank Professor Corey and the wisdom of all of you here. The education I got at CSU as a student has really helped me to do a lot of things I do. So said that, I want to ask this question now. So most of my research have been, with all the influence I have here, trying to question the models. So I do very careful experiments using very interesting systems. So in this case, actually, your percentage is really, really good, because your percentage shows that you don't want to rely on models only. You need to understand the fundamentals of processes and how the processes are manifest at different scale, etc. So my question is that the word validation is sort of overused, and that there's a calibration is misused in some ways. So in this particular presentation, you didn't mention anything about validation or calibration.
We haven't tried to,
Right? So
because we don't believe we can. Because we can never, we don't believe we can ever characterize the aquifer, the fractures in particular, with enough detail and enough confidence that we could put the actual pattern of fractures, matrix blocks, and so forth into our model, which would be required if we were going to try to actually validate it. But what we have done is the one I showed, where we try to go out in the field and see if our calculations give us the same order of magnitude as what we see in the field. And that has been successful. I didn't show any of the slides that I could have about how the models match up that jagged line. They don't match it exactly either, but it shows the right style. It's the right character, so we think we're on the right path. I might just point out that TISA is a very prominent groundwater hydrologist in his own right. He holds a chair position at Colorado School of Mines.
now that you went to school there.
Yeah, I did. I think it's time, right? I don't know what time it is, but it must be getting late.
Can't sit down. So Dave, I want to thank you for a great presentation, even to a poor structural engineer. I actually got many meaningful and good things out of your talk. Thank you. Just as a small token of this event, I actually have a statue I'd like to give to you. And it just commemorates this inaugural lecture of the Art Quarry Lecture Series. So, Dave, thank you very, very much.
Well, I appreciate this.
And Dave, there's also a certificate in here in the honorary information. Just follow up on it. Thank you.
Oh, you're all very kind.
So I would like to just have a few housekeeping comments. So if I could, Dave and Art and John, if you would join me at when we conclude the sort of presentation portion of this lecture, we'll get some photographs taken. I would also like to encourage you to stick around. We have this room till 7:30, and I want to thank again Engineering Analytics for sponsoring the reception and for all of you showing up here to celebrate this great talk and to celebrate Art Quarry as well. And lastly, Bob Langenbach, would you please stand up? So Bob brought to my attention that the Colorado Groundwater Conference is being held in Denver this Friday, focused on Colorado groundwater issues. And Bob's able, for the students that are here, if you have interest in attending, to get a discount, and you have some flyers. So if you're interested, please see Bob before you leave here this evening. So if I could, maybe one more round of applause for our speaker this evening. Dave, thank you very much.